Yep.
Well, good afternoon, ladies and gentlemen. We are the group 4, which includes Panina, Muhammad, and Ms. Stepan. The topic of our project is analysis of different human avoidance metrics while learning local planners for human-aware navigation in indoor environments. So, well, let's start step by step. So, what is the human-aware navigation? Well, nowadays, more and more robots are becoming part of our lives. So Ceres Robotics is about robots that help people by doing routine, remote, dangerous, or even repetitive work, including housework. They often work in the same space as humans. And I'm talking about, for example, delivery and cleaning robots. To avoid collisions and successfully complete their missions, these robots must take into account the movement of people around them. Specifically, their path planning or control modules should be human aware. In general, mobile robot path planning is divided into global path planning, which is responsible for generating a road for the robot to follow, and local path planning, which returns velocities for the robot to apply to follow actually the road. At the moment, research in human-aware path planning was done for both global and local path plannings. However, in most of works, the human awareness metric is represented as a circle of fixed radius, which the robot is not encouraged to cross. So you can see it in the center of the slide. In some researches, other metrics were applied, such as, for example, Gaussian function or other complex shapes that consider at least human orientation. So the problem is that in each paper, only one human avoidance metric was applied without any comparison. So to compare the human avoidance metrics between each other, we decided to choose one paper, actually about learning a local planner for a mobile robot, and we decided to do the following steps. So the first one is to resurrect the simulation done by researchers in the field of deep reinforcement learning, local planning. Then we put the simulation inside Docker image, so we can run it on different computers with different operation systems. Then we got same deep reinforcement learning models. We got the same models as authors. Then we performed literature review on other human awareness metrics that exist in this field. When we chose 3 of them and implemented 3 of them and trained corresponding agents. As a result, we compared these 3 chosen metrics by quantitative analysis.
So our project is prepared in robot operation system environment. We used PetSim ROS package in order to simulate pedestrian movement on the scene, and the flat-land ROS package for creating the scene with obstacles. The simulation of the environment for the agent is prepared in RVIS tool, where the pedestrians are presented as moving legs with the help of the pedestrian plugin. You can see on the bottom picture the description of the difference in acceleration and velocity for each leg during walking. Next slide, please. In the project, we use deep reinforcement learning approach to train the agent to avoid obstacles and pedestrians and reaching the goal. For that environment, we use proximal policy optimization from stable baselines package implementation. As the observation for our agent, we have waypoints from the global planner, road data scans from 2D LiDAR, and human velocity orientation and position from PetSim package. It leads our state space to be continuous. The possible action for the agent is 6 discrete actions with all combination of different translation and angular velocities. The reward function is present on the next slide. And so we move on. Yeah, the reward function is the sum of 4 elements, which is responsible for different situations during the agent moving. The first summon contributes with the high positive constant if the position of the robot reaches the goal position within the radius d. The second summon is responsible for awarding the agent while getting closer to the next waypoint and punish it if it drives away from it. As the first summon, is responsible for the obstacle avoidance and pedestrian avoidance, where the pedestrian avoidance metric is just the restricted circle area near the person. It is exactly what we wanted to improve. And the last reward element is the penalty for not moving at all. The next slide, please. In our project, we consider 3 different shapes of pedestrian avoidance metric. The first metric is the complex shape, where the shape is considering the pedestrian orientation. So the penalty for the robot depends on the area where it drives. The second asymmetric Gaussian social model considers the dynamic parameters of the robot moving, exactly the velocity and orientation as well. So this metric allows robot to move behind the person, but to not cross the path in front of the pedestrian. The symmetric Gaussian social model has a fixed parameters and considers only the orientation of the pedestrian with the offset of 0.2 meters in the front of the person. So it is shifted. With each of the pedestrian avoidance metric, we trained the agent. Let us see the experiments, what we have prepared. Next slide.
Well, now for our experiments, we performed the quantitative analysis for 500 episodes, and for that we used 8 different metrics computed for each episode. So let's start with the first 2. Next slide, please. So the success rate. It simply returns 1 if the episode was completed successfully, and 0 otherwise. For the time exceeded rate, it returns 1 if the robot exceeded the timeout in the episode, and 0 otherwise. Let's see the results. Okay, so the success rate was almost equally high for complex shape and asymmetric Gaussian metrics, but it didn't outperform the original metric. While as we see in the time exceeded, all implemented metrics demonstrated a significantly lower time exceeded than the original metric. Now, for the other metrics, we have the next slide, please. The success drive rate and the path ratio. So for the success drive rate, it simply returns a percentage of the successfully followed part of the global path, while the path ratio, it returns the path length ratio of the driven path to the global one in the episode. Now, if we want to see the results, we can see that the success drive rate was almost equally high for complex shape and asymmetric Gaussian metrics, but also it did not outperform the original metric. The path ratio was less for the asymmetric Gaussian metric, but it didn't perform the original metric. Now, let's discuss the minimum distance to pedestrian. So the minimum robot pedestrian distance, it returns the minimum distance from the robot to pedestrians in the episode, while the average returns the average distance from the robot to pedestrian in the episode. And the results, we can see that, next slide, please. We can see that the minimum distance to pedestrian was almost equal for complex shape and asymmetric Gaussian metrics. The symmetric Gaussian showed much larger value, and all values are larger than the original metric. Now, for the average distance to pedestrians, it was less for complex shape metric, and all implemented metrics showed larger values than the original metric. The last 2 metrics we have are the cumulative heading change and average heading change. The cumulative heading change returns the sum of changes in the robot's direction in the episode, while the average returns the average changes. Now, let's see the results. as we can see here, all implemented metrics showed less cumulative heading changes than the original metric, and it was almost equal for complex shape and asymmetric Gaussian metrics, but much less for the symmetric Gaussian metric. Average heading changes was almost the same for all compared metrics. Now, in the conclusion, we can see that this is a conclusion for all the results we said in the previous slides, as we can see here, like we ran the simulation performed by the original paper, the DRL local planning, and we got the same results as the authors. Then we implemented the proposed human avoidance metrics and analyzed the results quantitatively. Now let's move to the future work with my colleague Stefan.
Yes, well, we successfully have proven that our metrics work. However, we still believe that we can achieve better results with more agent trainings and actually by tuning parameters of the implemented metrics, because they have the many parameters to tune. For example, Gaussian functions have at least 2 of them. Also, the complex shape can have different values of the circle around the human and for the area in front of the human and behind him. We want to learn more about metric learning to gain some awesome weights for summations of the reward function, and to gain them in an automatic way. Because now it is a problem too. We use different weights for different summations, and maybe metric learning can help us with it and to improve the agents. So, yeah, well, thank you for attention. Now we are ready to answer your questions.